Bismillahirrahmanirrahim. Welcome back to the class of real analysis. We are using Principle of Mathematical Analysis by Walter Rudin, and our discussion is continuing on chapter number 3, Numerical Sequences and Series. In the last lecture, we discussed concept of convergent and bounded sequence. Inshallah, in today's lecture, we will discuss a very important theorem, Theorem 3.2. This theorem is related to convergence of a sequence and boundedness. So before going to start the theorem, we will use some basic definition, that is the neighborhood of a point, that actually we discussed in chapter number 2, the topology. Neighborhood of a point, how can we define this? This definition says a neighborhood of a point P is a set NRP. Neighborhood of a point is always a set. This set consisting of all points Q that satisfy this condition, that is the distance of point P from Q is always less than some real number R, where R is a positive real number. The number R is called the radius of this neighborhood of set. So simply the neighborhood of a point P is always a set that can be formed by this inequality or satisfy this condition. In other words, we can say that the set NRP is called neighborhood of a point P if there exists an open ball B whose center is at point P and radius is R, such that it contains P and contained in the neighborhood of point P. That is, P is the point of your open ball, and this open ball is contained in this set. Then we say this set N is neighborhood of this point P. So we will use this definition in the proof of this theorem. This theorem has 4 parts. Theorem says, let Pn be a sequence in a metric space X. Pn converges to a point P belong to X if and only if every neighborhood of a point P contains Pn for all but finitely many n. Firstly, understand this line. This is very important. For all but finitely many n. In last lecture, we discussed the definition of convergent sequence. This definition says a sequence Pn converges to P if it satisfies this inequality, that is the distance of this point Pn from point P is less than epsilon when your n is greater than some positive integer n. So this inequality hold after some stages. For example, if you take n is equal to 100 and you say this inequality hold for some positive real number epsilon when your n is greater than 100. So for every n that is greater than 100, this inequality hold. It means this inequality hold for finitely many n. This inequality hold for all. But finitely many n mean this inequality does not hold for when your n is less than or equal to 100. These are the finitely many n's for which this inequality does not hold. But this inequality hold for all n other than or beyond this n. So in first part we have to show Pn converges to P if and only if every neighborhood of P contains Pn. Suppose we suppose that Pn converges to P, and let V be the neighborhood of point P. Then by definition of neighborhood that we have discussed here, there exists some positive real number epsilon such that this open ball whose center is at point P, that can be formed by the distance of point P from Q, where Q is the points in the metric space X. This distance is less than epsilon. This form the open ball is contained in V. This implies Q belong to V. How Q belong to V? Because Q is actually element of X, and it satisfied the definition of this definition, and this is the definition of neighborhood. We have defined the neighborhood of in such a way. A neighborhood of a point P is a set of all points consisting of all points Q such that distance of P from Q is always less than R. In theorem, I have replaced R with epsilon. So this consists on all those points Q that satisfied this inequality. Automatically, this point Q belong to the neighborhood of this point. What we have to show? We have to show that if Pn converges to the point P, then every neighborhood of point P contain Pn. Since Pn converges to P, for this epsilon, next we have to show. Now we have to show that this Pn converges to P. Pn belong to P here. Since Pn approaches to P, for this epsilon, there exists an integer n such that this inequality hold for all n greater than or equal to n. This shows that this inequality shows there exists an open ball whose center is point P, and this point Pn belong to that open ball. As this open ball is a subset of this neighborhood V, this shows that Pn belong to V. That is our target. Conversely, we suppose this definition hold for suppose that every neighborhood of P contains all but finitely many of the Pn, and we will show that Pn approaches to P here. Take any epsilon greater than 0 and we define the set V such that this consists on all points Q of set X that satisfy this inequality. This is simply the open ball B whose center is at point P with radius epsilon, which is the neighborhood of point P here. By assumption, there exists an integer n corresponding to the set V such that Pn belong to V if n is greater than or equal to n. This shows the distance of Pn from P is less than epsilon for all n greater than or equal to n here. And what does this show? This shows that Pn converges to P. This is the definition of convergent sequence that we discussed in the previous lecture. Its B part. In its B part, we have to show if P and P prime are the two elements of set X, and the sequence Pn converges to both P and P prime, this shows that both are equal. In other words, you can say this theorem says that the limit of a convergent sequence is always unique. This is the other statement that can be used for this part. So to prove that P and P prime both are equal, we will show that their distance is always less than for every positive real number epsilon, because at the end we will say as epsilon is any arbitrary positive real number. So whenever your epsilon approaches to 0, then the distance between P and P prime approaches to 0, and hence they are equal. So firstly, we use a definition of convergent of sequence for both of these limits P and P prime. So when you say Pn converges to P, then for some positive real number epsilon, there exists an integer n such that the distance of Pn from P is always less than epsilon by 2 whenever n is greater than or equal to n. Similarly, in case when Pn converges to P dash, there exists n dash such that this now it will be a another integer n dash, such that the distance of Pn from P dash is always less than epsilon by 2 when your n is greater than or equal to n prime. Say this is inequality number 1 that contains an integer capital N, and this inequality number 2 that contains n dash. We take the maximum of these two numbers is denoted by n naught, and using the triangle inequality, as we have discussed, that I have to show this distance is less than epsilon. So I will use the triangle inequality for this expression. So d of p and p prime can be written as this is less than or equal to distance of p to pn, and from pn to p dash. By involving pn in both parts, we can make the triangle inequality. By using 1 and 2, this part is less than epsilon by 2 and this is also less than epsilon by 2. As we have taken n naught as the maximum of these two numbers, so now we will write here n greater than or equal to n naught. This shows that the distance of p and p dash is less than epsilon for all n greater than or equal to n naught. And since epsilon is greater than 0 and it is an arbitrary real number, so we can conclude that this distance can be equal to 0, or we can say that they are equal. C part. This is also very interesting. This shows that this says that if your sequence Pn converges, then the sequence is always bounded. This is very important part. This says that every convergent sequence is a bounded sequence. Every convergent sequence is a bounded sequence. Since Pn is convergent, so it must be that there exists some limit of Pn. So we say, suppose Pn converges to real number, some number p. Then by definition of convergent sequence, for all epsilon greater than 0, there exists an integer n such that it will satisfy the definition of convergent sequence. This distance is always less than epsilon. For our convenience, we are using epsilon equal to 1 here for all n greater than n here. Now this is the important and crucial point of this part. If you focus on this expression hold for all n that is greater than capital N. Suppose I say my n is 100. This shows that this expression dp and pn, this is less than 1 for all n greater than 100. It means when you take n is equal to 101, this term p1, this is less than 1. Similarly, when you take 101, when you take n is equal to 102, again distance of p from p102, this is always less than 1. Similarly, if you take n is equal to 1000, this is always less than 1. So this shows that this tail, this sequence of terms which is greater than capital N, this is always less than 1. So I can say these all terms which are greater than n, n plus 1, p, up to so on, these all terms are always bounded by 1. Now what's about the terms which are less than n? Suppose these are my terms. This is my n. Now all the terms which are starting from here, these are always less than 1. Now what's about the terms which are less than here? That is the left tail. So we suppose the terms which are on the left side of n obtained by the distance dp1 from p, dp2 from p, up to some dpn from p. These terms and 1. Suppose the maximum of these numbers is denoted by r. So this shows that the distance of the sequence Pn from P is always less than or equal to this number r uh, for all n equal to 1, 2, 3. So this shows that the sequence is bounded. Uh, in previous lecture we discussed that a sequence is called bounded if its range is bounded. In term of metric we say a sequence is bounded whenever every term of this sequence if the distance of every term of this sequence is always less than some real number r, positive real number r. So this shows that your sequence is bounded by r. D part. This says if E is a subset of X and P is the limit point of E, then there is a sequence Pn in E such that P is the limit of this sequence. Firstly, how can we define the limit point of E? A point P is a limit point of the set E if every neighborhood of P contains a point Q other than P such that Q belong to E. For example, suppose this is my set E. P is called limit point of E if every neighborhood of a point P. Suppose this is a neighborhood that is n1. Suppose this is my first neighborhood of that is denoted by n1 and contain P. Now P is called limit point of E if every neighborhood of n1 must contain a point of E other than P. Suppose there is another point Q here which also a point of E and it belongs to n1. Similarly, suppose there is an other neighborhood of this is my neighborhood of n2. This also contain a point P. Now it must be that n should also contain a point other than P. Suppose this is R point. So a point P is a limit point of set E if every neighborhood of P contains a point Q other than P such that Q is a point of E. Now I have to show that if P is a limit point of the set E, then there exists a sequence Pn. In E. So to prove this result, firstly I will show that there exists a sequence Pn in E. This is our first target. Then secondly we will show that this sequence has the limit P here. So to prove, I will show firstly Pn is a sequence that contained in E, and then I will show that P is the limit of this sequence. So let us start here. Since P is a limit point of E, then by definition of limit point, every neighborhood of point P contains a point of E other than P. This is the simple definition of neighborhood. Now for each positive integer n, consider now for our convenience I am going to construct here an open ball such that for each positive integer n, consider the neighborhood defined by whose center is P and radius is 1 over n. Because P is the limit point of E, there exists a point Pn. For each n, there exists a radius 1 over n. For example, when you take n is equal to 1, there is a point P1 belong to E, and for this I have a radius 1 over 1, that is 1. Similarly, when you take P2 belong to E, there again a radius 1 over 2, 0.5. So continuing this process, for every point Pn belong to E, we can find some radius 1 over n. As whenever you increase n, your radius approaches to 0 and you becomes closer and closer to point P here. So such that so in this case when you becomes closer and closer to point P, then the distance of this point Pn from P is less than this radius 1 over n. In other words, I have used only the definition of here of open ball here. When you say p, this is open ball whose center is p and radius is 1 over n, and now you say if pn belong to this open ball, then by definition of open ball, the distance of these 2 points will always less than 1 over n. As this inequality hold for every n, so thus we obtain a sequence Pn of elements that belong to E. Next, we show that this sequence Pn converges to the limit P here. Let epsilon is greater than 0 be a given number. We choose n such that this 1 over n is less than epsilon. We cannot choose 1 over n greater than epsilon, otherwise it will not work here. So it forcefully we will choose 1 over n less than epsilon. Now, by the definition of convergence of sequence, the definition of convergent sequence says if dpnp is less than epsilon, if n is greater than n. So that's why I am taking here n greater than n. We cannot take n less than or equal to n. This is beyond against the definition of convergent sequence. So when if n is greater than n, then after taking reciprocal, this become 1 over n less than 1 over n. Since this distance is less than epsilon that I have from here, this distance is 1 over n, less than 1 over n, and further your 1 over n is less than 1 over capital N. So this becomes, this distance is less than 1 over n, and 1 over n that I have forcefully set here, 1 over capital N is less than epsilon. This shows that this distance is less than epsilon, and this hold when n is greater than n, and it fulfills the definition of convergent sequence, and hence Pn converges to P here. So I hope now you have a clear understanding about the concept of this theorem. In this theorem, I have used only the concept of convergent sequence, bounded sequence, and limit of a sequence. If you have a fully grip on these 3 concepts, I hope you can easily manage this theorem. So if you find this video helpful anyway, kindly please like, share and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.